Hi, just a quick update on the VHDL 6526 CIA IC for the Commodore 64. I have made a top level which then connects together all of these other entities. So all of these are entities anyway, but this one has all of these modules. And a test bench. And the cool thing about the test bench now is that I'm using procedures, and procedures, you can see them on the top here, they look like functions. They have parameters, and yeah, so you can send parameters to it, and then it will do code on it in a sequential manner. So for simulation this is great, because then I can say in the test bench, set the clock signal low, wait 100 nanosecond, set the address bus, and I know the PLA is maybe 10 nanosecond delay, so then after the address is set, then I know the chip select is coming a little bit later, and so on. So, and also you can send the direction. So I have a couple of these procedures, and this is just a no operation procedure, as if the CPU is not executing any code. And I have a reset procedure, and you can see here what's going on. Here is the actual unit under test. That's the whole design actually. It's the CIA with the structure architecture. So yes, and we have a port map, so we connect all those pins together in the test bench. Here you can see the stimuli process. So first on the top there you see we do a reset, then the CPU is doing nothing for one cycle. You can specify how many cycles you want. That's what I've done here. And then I'm writing several things into the register, so 0 is write and 1 is read. And this is the address, so timer A low, timer A high, control register for timer A, and this is port B control register. So port B is set to all outputs, and then on port B it's also set to high on all outputs. And then this is a bit tricky though, because in the timer control register A we also can control what comes out on port B on pin 6. So by setting this bit, third bit, or second bit actually, from 0, we get the timer underflow out on port B. So let's have a look at that in the simulation. So see if I can do this with one hand. No, I can't. Hold on, sorry. I don't think I will edit this video, so I will just please just bear with me. Here you can see all the first we have a reset, then we have some no operation cycle, and then you could hold on there, that's much better. And you can see the RS is F045E31E and so on. That was what we had in the test bench. And you can also see I put stuff on the date bus. And now we can see what happens on the outputs. For example, this is port A and this is port B. And you can see initially the port A and B are all inputs. So H, that means it's like a weak pull-up. So, and when I write FF into 3, that is port B direction register, we get outputs, because we say all pins on port B are outputs. So you see they turn into outputs. and they are initial 0, so, and then we write FF into 1, which is port B. That makes all port B high. This is the one I said that was tricky. I have to go into timer A, and you can see timer A. I'm not looking at all stuff inside timer A here, but what 3 means is that we want PB on. So what that means is that when you get an underflow, let me find the underflow. There's an underflow. You can see underflow flag down there. You can see when we get an underflow, we also get it out on port B, bit number 6. And after a while I also write something to the device. As you can see here, I write 1, that means start timer, and since it's not 3 anymore, then it's no longer PB on. So you can see that these underflow bits, they are still coming out here, but no longer coming out on the port. So that's cool. Let's see something else I'll do. Yes, here I'm turning on the mask register for timer A underflow, the interrupt mask register, so such that the IRQ will now go low when we get an underflow, and it does. And I also had done something in the test bench to make the CPU read the interrupt register, because when it reads the interrupt register, if it reads the correct interrupt register, it will then disable the IRQ. So it does so. That's great. And the value out when it reads is 1. You can see ship select comes, and we have read high. That means we have a read, so the value that comes out of these ones. So the first bit indicates that it's the interrupt that has occurred. It has to check that, you know, is an timer overflow. So let's get out here, and I also start the clock. You can see that I have the TOD time of day clock now. So I set it to 9, so that's 12 PM I think. And then after a while it will then, yeah, if I go out there you can see that it goes to 0001. And then I also earlier, if I go back, you can see that I also set, yeah, it's a bit difficult to do that live now, but I also set the alarm to 0001 PM. So, and therefore, when you have the alarm on, and you also have set the interrupt mask for that bit. Let's see if we can find that actually. Let's see. That will be the D register, so we have to write. These are just random interrupts anyway. No, just move out. See? I think I do it here when I set up the time, and then I also set the alarm at the same time. You can see on the top there, there's a lot of activity. That's I'm setting the clock, and then I set the time. So there, in, go back. It's easier when I have two hands, because then I can just point them also. BA98, that's the time of day, or the alarm. It depends on what's in the D register, bit number 7, which is active when it says 8 there. So when I set it to 0 here, I write time of day, and when I set it to 84, I don't remember exactly what 4 was. I think no, sorry. Okay, Okay, I have to figure that out. I don't remember anyway, but when I say F to 8, this is not going to be the best video. Okay, so F, down here you can see what F is, and 8, that's that's the CRB alarm bit. Then if you go to the top of this document, I've written that the alarm bit, which also goes out of the timer bay B to the TOD module, is forwarding to TOD. So when we set F to 80, we are setting that the next write to the TOD is supposed to set the alarm. So we set the alarm to 81. That means 1 PM, I think. So that's why we got that alarm. But that's not enough. You have to also write something into the register here. So it's a bit weird how that works, that the interrupt mask register, you don't actually write directly to the register, you set bits. So the first bit of the whole string, I can show you that if I expand dB here, you can see the individual bits. So you see the 7th bit on top there. Now if you set the first bit, then you say clear the first one, because that's one's one. Had it said 0 there, then the first bit would have been cleared. So you can clear individual bits in this manner. So if we go to here, we say 84, that means you want to clear, or actually set the bit number 3, which is the time of day. So since this video is running anyway, I can go into the interrupt now. You can see that the first bit in the mask is timer A, B, and then you have the TOD alarm on bit number 2. I said 3, but I meant 2 from 0 actually. Yeah, so that's why the IRQ is going low. And let's see. Here's the IRQ, yes. So, and when it reads out, it's usually it just says, hold on. It's 30 minutes already. Anyway, yeah, it says 4 seconds there, and then it has like 6 clock cycles before the IRQ is read. That's something I did because I know the CPU has take some time to put things on stack and such, so it's not important for the simulation, but I thought it was interesting. And here we have a read from the CPU, and the value is 81. That means there's a timer A interrupt. But now if we go up, if you just look here now when I scroll, you can see that it goes 6, 7, 8, 9, 10, then we should get an alarm. And we do, because we get an IRQ, but we also get an underflow. That's interesting. For now we have 2 interrupts at the same time, or in the same IRQ. So when the CPU reads now, it should see 2 interrupts, not 1. So there you can see we have actually 2, because 85, that's bit, let's see. Yep, that's bit 1 and 2. They are high at the same time. So that's really cool. So it's working rather well. So I don't remember, it was something else I wanted to show you. There are more things in here. I want to test this serial port. I haven't tested that. I have tested that individually together with the timer, but it needs more testing. So yeah, so when I made this CIA SDR, the structural VHDL, I can show you that. it was basically you just copy paste all the ports. You see the CIA entity has a set of pins, and then you have timer A has a port, just a copy paste from timer A actually, and then timer B and such. So you can go on forever here. And then time of day, which is the last, and on the top layer also make this read and write signal out of RV. So that's the ship's access control. That's all there is actually. And then we start to instantiate all the modules. So therefore you say the instance name, entity, the library which it's residing in. Timer A is the entity name, and then the port map. So you connect all these signals into or directly on the port. So there was a lot of work to make that work. There is a diagram of all of this, but it's not actually showing everything in the datasheet, how they are connected together. So that's all there is on that layer. So when you get to test bench, then you take that CIA again, like I said in the beginning, and instantiate that. So you get all those in the correct hierarchy. I don't know how you say that. Hierarchy. Yeah, the structural hierarchy. Please help me out here. Yeah, okay, thank you for watching. 60 minutes, 70 minutes already, so hope you liked it. It was supposed to be just a update on it, so yeah, it's really cool actually that it's coming along like this. Okay, thank you for watching, bye bye.